All right, good afternoon, everyone. I'm David Beckingsale, and Rich Hornung was just setting up the laptop. So yeah, for the next hour and a half, I think it is, we're going to be talking to you about the Raja programming abstraction, which we develop at Lawrence Livermore National Lab. So today, this is kind of a tutorial introduction overview on how to use some of the key features in Raja. So we have the kind of standard parallel loop execution, which I guess you will have seen a lot about in the Cocos tutorial just before us. So we have kind of simple loops and then some more complex stuff where if you have nested for loops, you can parallelize those and do some transformations and things. We have reduction operations, so you can do safe parallel reductions. We also have atomic operations and scans. And then we're also going to cover kind of some of the more philosophical stuff behind Raja, so the motivation and goals for the project, and a few application considerations, things that you might want to think about if you're developing an application and you're going to be targeting kind of heterogeneous architectures. So we do have a user guide that's on Read the Docs that has a few more things that we're not going to be able to cover today, a complete overview of all the features. You can get to that this URL, which is obviously pretty difficult to type right in, but we have everything hosted up on GitHub, and this also has links to all the other stuff. So all the code examples you're going to see today are in the examples directory in our repository, and you can get to that. That's the URL. Pretty simple, llnl/Raja. And we have these other materials related stuff. Like I said, this is all linked to from the GitHub project. So we have the user guide, which is the Read the Docs site with kind of the complete documentation. We have a performance suite, which is kind of a set of benchmark kernels that we use to monitor performance for all this stuff. We have Raja versions of a few different proxy applications. And we also have the Chai project, which is kind of a managed array abstraction that moves data around for you based on where you're going to be executing different Raja kernels. I guess this is kind of a standard thing, but if you have any comments, questions, suggestions about the slides and the material that we have today, we'd really appreciate you letting us know. We have a Google group that we link to on the GitHub project, and we also have an email list that goes to the whole Raja development team. So feel free to shoot any comments there. And obviously, during the presentation, if you have any questions at any time, please stick your hand up and ask. Yeah?
So we just heard about Cocos for 1.5 hours, and I haven't used either Cocos nor Raja before. So do they have the same goal, Cocos and Raja? Are they the same idea, just developed in two different labs?
I think they're two solutions to the same problem, would be the most diplomatic way to put it. And I think you might understand more after seeing, the syntax differences and some of the differences in the two models, which one might be the best approach for a particular problem. And I might let Rich speak some more to that a bit later. Yes, so we'll start with the most basic example, just a really simple loop. So this is just a DAXP operation, or it's vector multiplication and addition. The C-style loop hopefully is fairly familiar, right? You looping from 0 to n-1, doing the computation. So if you convert that into a Raja loop, the range that you're iterating over becomes a range segment, which is just these contiguous indices from 0 to n-1. The actual for statement is replaced with a call to Raja for all. And the loop body stays the same, but we put it inside a lambda function. And these are kind of the four core elements for this Raja loop execution. So you have the template, which is the actual what you're going to be doing. So in this case, it's for all. There's a policy which determines how you're going to be doing it. We have the iteration space, which controls what indices the loop's actually going to be running over. And then we have the loop body, which again is just a lambda function. So the for all method is just going to run like a parallel for, or it could be a sequential for, but a for loop based on the execution policy type. So this could be something like sequential, OpenMP, CUDA. We pass in, as the first argument, an iteration space object. So the range segment was just this contiguous range of indices, and we have a few other types that I'll get into a bit later in the tutorial. The loop body is a lambda function. So it's this closure that has some function with a data environment, and the argument that we pass into the lambda function is always the loop variable. So like in this case, it would be the elements, the indices taken from whatever iteration space you're passing in. And these four pieces are going to come up again and again as we go through the tutorial. So I've already said that by changing the execution policy, you can change the way that the loop is run. So we have, and these are different types that will instantiate that function for the different backends is what we call them. So SIMD would do this kind of like try and force that loop to vectorize. OMP parallel for would use OpenMP, like the parallel for pragma internally to distribute the loop over threads. You have things for CUDA, OpenMP target, which is kind of the OpenMP 4.5 constructs to run on a device. And then we also support Intel's threaded building blocks. So, and in addition to those, we have a couple of work in progress backends, which the OpenMP target is one of them. We also have a backend for running on AMD GPUs as well. And this is the kind of the stoplight chart of how well everything's working across all the different backends. And we have these stoplights for every kind of set of features. So after that simple example, just kind of step back and take a bit of a look at the motivation and goals behind the project, and maybe this might answer your question a little bit. Obviously, we're targeting portable parallel loop execution, and one key focus is that we're doing this to enable portability in existing applications without completely disrupting the programming style of the application team and the algorithms that they've already written. But obviously, this could be a model for new applications so that they can be portable from the inception. And obviously, the building block of this is the parallel for kind of idiom. The key points that we kind of try and really stick to are that you should be able to keep single source kernels if you can. Should be easy for application developers who aren't necessarily computer science or parallel programming experts to grasp the different concepts and constructs that we provide. You should be able to incrementally and selectively use Raja, so if there's one piece of your application where it really makes sense, you can throw Raja in. If there's something else where you don't want to spend all the time porting for minimal gains, that's not a problem and you don't need to. Like I said in the previous slide, we want to really avoid any major disruption to an application source code. Lots of applications using Raja have decades of investment, right? You can't really tell the developers that they're going to have to completely rewrite their application to run on a new architecture. We try and make the implementation flexible via encapsulation, so with things like the different iteration spaces and the execution policies. Those types, the execution policy types, make it easy for you to parameterize different pieces of your code. So you could use a different execution policy depending on the loop that you're running, and that lets you kind of systematically tune your code for better performance. So the next thing is going to be reductions, and the whole point of the reduction types is to hide any of the complexity of the kind of parallel reduction algorithms and implementations, right, with it, and you just don't need to worry about it. And the semantics always look the same, regardless of where you're actually doing the reduction. So our example here is just a dot product, right? It's fairly simple. But then the Raja version uses a reduced sum object, and this class of objects are the Raja reductions. And you can use that just like you would a normal kind of scalar variable, but perform the reduction into it, and the object kind of hides all the reduction mechanics and ensures that's correct regardless of where you're running. So each reduction requires a policy, so that tells us how we should be reducing things, the type of the value, so like a float, a double, or integer, as well as an initial value. And for each of these reduction objects, the way you would update the reduction value is kind of what you would expect. So for sums, you can use plus equals. For a min or max reductions, we have a min and a max function. The one thing that makes this different from just using, like your regular type to do the reduction is that after the Raja for all loop, you call a get method to get the reduced value back from the reduction object. You can also do this if you cast it back to the type, the underlying type of the reduction, just as kind of like a sugar type thing. The one thing to note here is that the reduction policy and the execution policy are separate, but they must be compatible. So if your execution policy was CUDA and your reduction policy was SIMD, it's not going to work, right? So you have to make sure that you coordinate those so that things kind of function correctly. And we provide reduction policies that map to all the different backends that you can use for the kind of for all execution. So we have sequential, OpenMP, CUDA, the TBB, and then OpenMP target reductions as well. And the same for SIMD, OpenMP target, and the ROCm backend, which is for AMD GPUs. They're still kind of works in progress. The 5 different reduction types that we support are the 5 most common that we've seen in our applications. So that's sum, min and max, and then there's min-loc and max-loc, which also, they give you the index where that value was found. Yep.
So the reduction policies, when you say that one reduction policy, for example, is OMP reduced, doesn't mean that on the back end it's exactly the same reduction that OpenMP does, and therefore you would always support exactly those data types that OpenMP reductions support?
No, and the reason for that, which it actually kind of is highlighted in this slide, when you are doing like those OpenMP reductions, right, you have to put the reduction variable in the pragma, which doesn't jive so well with the lambda mechanics. So the reduction implementation that we provide for OpenMP is a custom implementation. It generally works for like the native types. I'm not sure if you can do it with user-defined types.
Separated from what's in the lambda itself, right? So.
And would it support any data types when you overload the operators?
We've tried some different things, but that I'm not going to say we support it in general. It has worked in a few instances where people have tried it. We are also thinking about alternative implementations to this to make this a little bit more flexible and powerful, in which case we may be able to directly use, for example, the OpenMP pragmas directly inside the Raja implementation. But that's kind of down the road.
Yeah, so one of the reasons that we use the reduction objects, right, rather than trying to jam things into OpenMP pragmas or whatever, is because you really to implement that, you would have to pass every reduction variable as an argument to the for all function, right? So in this case, there's only 5 reductions, but we've seen loops with tens of reductions, and it's, if you're to convince an application developer to do that, it's kind of a hard sell, right? So with the Raja reductions, you can capture as many of those reductions in the lambda as you want, and that will all be correct as long as those policies are compatible. So this is just a quick example. So suppose we run that code on the previous slide where you had all the different reduction types going at once over a vector where you just have this alternating 1, -1, and then in the middle you have -10, 10, -10. You'll end up with a sum of -9, a min of -10, max of 10. Then for the max loc, you'll get n over 2, but for the min loc, you could get n over 2 -1 or n over 2 +1. Because if you're doing this in parallel, it depends, either of those is correct, but it might not be the semantics that you expect. So we do have these reproducible reductions where you run it and you're always going to get the same value regardless of how the threads or whatever have reduced the value. So our kind of traffic light chart, the reductions are all fully baked on the sequential OpenMP CPU, CUDA and TBB backends. Then we have some work going on to get SIMD, OpenMP 4.5 target and the ROCM reductions up and running. All right, the next section is about the iteration spaces. So this is that object that you can pass into the for all that determines the set of indices that you're going to be running your loop construct against. So a segment is the basic way to define the iteration space for a loop. And it's just a set of loop indices that are going to be run as one unit. So you can have a contiguous range, a strided range, or a list of indices, which is kind of like an indirection array. And then you can group segments of indices together into an index set container, which is just a number of these segments. And then you can run all the segments in an index set with a single Raja for all loop, and it will run it against all of those. So the simplest type that we've seen already is a range segment, and that's just a contiguous sequence of indices that's stride 1. So in this case, if you make a range and you construct that with 0 and n, the indices that you're actually going to run are 0 to n minus 1. The second segment type that we have is a range stride segment, and that's just a strided sequence of indices. And then, so when you construct one of those, you can pass in the stride as the third argument. So in the first example, you pass in 0, n, and 2. It's going to run 0, 2, 4. It's just striding by 2, right? And you can also use the range stride segment to have negative strides, right? So going from n minus 1 down to 0 by passing in -1 as the stride. And all these segment types support negative indices. So if you're kind of indexing or iterating in your kind of native coordinates, it's fine, you can have negative indices. So these segments are actually templates on the type of the index that gets passed into the loop body that we have these aliases for that just use our Raja index type, which is a pointer diff type, which tends to be the best for compiler optimization. So how the compiler is going to optimize that loop, depending on what the type of the loop variable, that can break a few compiler optimizations. So we try and just optimize for that best case. But if you want to have segments of different value types, you can just make a type range segment and pass any type in there. So the third segment type we have is a list segment, and this is an arbitrary set of indices, which is kind of like an indirection array. So if you had an array of indices that you wanted to run over, rather than chasing through your array to find each index, you can just build them up into a list segment type. So in this example, if you have an array of indices, here's 10, 11, 14, 20, 22, and you build a a list segment with that array. When you run a Raja for all and pass that list segment in, it's going to run those loop indices, but you don't have to have any indirection code inside the loop body where you're like reading IDX0, IDX1, and so forth. So an index set is a container of segments, and it can be any of those segment types that we've just seen. So like in this case, you could build up an index set of a range segment and a list segment. And then when you put those segments in, the iteration space is partitioned into two contiguous chunks, the two ranges, right? So from 0 to 7 and 24 to 27. And then you have this list, which is just these arbitrary indices with space between them. That's 10, 11, 14, 20, 22. And you can pass an index set directly into the Raja traversal method, like the for all. And then you have a two-level execution policy. So you say how you want to iterate over the segments in the set, and then how you want to iterate over the indices inside of each segment. Right, so you could do something like parallel over the segments, but for each segment, you're actually going to be iterating sequentially. And this can be useful for kind of maintaining correctness of algorithms. So, and all our segment types kind of model this iterable C++ interface. So you need to have a begin, end, and a size, and provide two types inside the class. So you can have user-defined types that if they have these properties, you can use them as a Raja segment for getting those indices out of. So the index set concept is something that's kind of is unique to Raja, and this is just a little bit of why we actually provide one of these. So lots of the codes that we deal with use indirection arrays just to make the actual code that the application developer sees more simple and more general, right? But when you have this indirection, when each time you want to find the next index to run, you have to read it from an array, right? That impedes performance. It's adding instructions, and it can break lots of compiler optimizations. When you have a simple range where it's just a stride one kind of set of indices, it's a lot easier for the compiler to optimize, and you can get better vectorization and things like that. And the final thing, I kind of mentioned, but you can partition and reorder your indices so that you can avoid synchronization and make an algorithm that may not look inherently thread safe, but actually run it in a thread safe way without changing how your code actually looks. So a quick example of this on the next slide. So if you have something like this where you're accumulating these element volumes onto mesh vertices, right? That if you just run that in parallel, you're not going to be guaranteed that that's going to execute correctly, right? There's going to be conflicts. But you can partition all the different elements into independent subsets, which would be independent segments based on a kind of a coloring algorithm. And then you can iterate over the different colors sequentially, and then each element of the same color, you can actually run that in parallel. So in this case, each color, you have the sequential, and then you have the OpenMP parallel for the indices in one color. So those are going to be running in parallel. The loop body still looks exactly like how the domain expert would write it, but now it's able to execute safely in parallel. So all the segments and index set stuff is working across all the backends apart from the ROCm AMD backend right now. I'm sorry, I keep looking over my shoulder because I'm expecting the slide to be blank. But so the next construct I'm going to go over is the atomic operations. So these are just portable atomic operations that let you perform an atomic memory update, so a write or a read, modify, and write. And in some cases, they can be preferable to using a reduction. They just be easier, and they can be higher performance. So this is just doing a histogram. This again, like all of these examples, this is inside the repo in that examples directory if you want to take a look at the full code. But for this, it's just computing a histogram, and for each value in the A array, you can just atomically update the count for each bin in your histogram. Like all of our constructs, you pass in a policy, and this determines the actual back-end implementation that you're going to be using. So we have a built-in atomic policy that uses the compiler built-in atomics. And again, like with the reductions, you have to make sure that your atomic policy is compatible with the loop execution policy that you're using. So as well as the compiler built-in type, we also have an auto-atomic, which will just do the right thing regardless of what your execution policy there is, right? So you could swap CUDA for something else, and the auto-atomic would still do the right thing. This is kind of is a more portable option. We also have an atomic ref interface, which is more like the C++ standard atomic, which supports arbitrary memory locations and all atomic policies. So you have some double, and you can get an atomic reference to it and then operate on it like this. To provide a range of atomic operations, add, subtract, min, max, increment, decrement, some bitwise stuff. There's exchange and check and store, or check and swap, and we also have that standard atomic interface. So we have a lot more on this in the user guide if you're interested in more about the atomics. So on our little traffic light chart, we have atomics working on sequential OpenMP and CUDA backends. They're not available for SIMD or for Intel TBB, and they're a work in progress right now for the AMD ROCm backend. All right, so the next construct is scans. So this is another kind of building block of parallel algorithms, parallel for, parallel scan. And they're a nice primitive if you're converting serial operations to parallel. There's lots of useful applications, and we tend to point people at these lecture notes if you're interested in how you can apply scans. So the most common is a parallel prefix sum, and we have inclusive and exclusive versions. And so in this case, when you're running this scan, the output array will contain partial sums from whatever your input array is. So the in-place version will return the result of the scan in the input array, and you can put different operators into your scan. So the most common, as you said, is a sum, but you can do things like a minimum or a maximum. And if you don't pass in an extra operator, then plus is the default. And there's a bit more on scans in the user guide. Yep.
Why don't we repeat the in when we call this? It's in plus n.
The arguments are just two addresses, I think. Is that right? It's like a begin and an end. It's
address and an offset.
Yeah.
It's got pointer and offset.
Yeah. Okay. Yeah, and then so the scan support, we have it running sequential OpenMP on the CPU, CUDA, and Intel TBB. We don't have SIMD or OpenMP 4.5 scans, and again, you can tell that the ROCm AMD backend is a work in progress right now. That's actually the end of my section, so I'll hand you over to the R in Raja.
Cocos and Raja are kind of being developed in different environments for different sets of applications. Sandia has a very different kind of set of applications than we do at Livermore. Most of this stuff was built up in the weapons program at Lawrence Livermore, and there's very special kinds of codes that we have there. So I just want to kind of give you a little bit of background, take a step back and say, well, what's motivating this and what's driving why we do certain things certain ways, right? So we have these large multiphysics applications, and when we build an application, we typically integrate multiple codes together, okay, that do very different physics, right? But they have to work together. So each of those individual pieces has hundreds of thousands or millions of lines and many kernels. Basically, you know, taking a code, like one of our hydrodynamics codes, you know, has over 23,000 kernels in it. Putting something in, you want to be as minimally disruptive as you can, right? And make it easier for the users. This is true of all performance portability sort of models, but these codes run on laptops. We run on DoD machines, machines at Livermore. We run on commodity clusters, these advanced technology systems. And the ASC program, which is the Advanced Scientific Computing Program in the NNSA, program in the DOE, procures these large systems in 3 to 5 year cycles. But the codes live for decades. Our current set of production applications were started at the beginning of the ASCII era, which is probably about when many of you were, hopefully, were born. But maybe you were in elementary school or something. It started in 1994, and that was the last time we actually built new codes, you know, large codes, right? So, and these are used in production daily for decades, right? So the codes have to live over multiple platform generations, different types of technologies. So Raja kind of grew out of the need for a model to basically make those codes portable over to new architectures, right? And in addition, these codes are being developed continually with new modeling capabilities to run different kinds of problems. So going back to what David was saying, you know, these are the kind of points that we're trying to focus on. We want the single source kernels as much as we can, easy to grasp. Most of our code teams are physicists, chemical engineers, engineers of other sorts, mechanical, applied mathematicians, et cetera. They want to try it out in their codes, right? They can't have a model where they have to buy into everything, and it has to work with other models. Raja has to work with pieces of other codes, and we have examples of this where they're using Cocos, or they're using OpenMP4 directly, or they're writing just in CUDA or whatever. Features that aren't found in some other models. The index set stuff in particular, and some of the stuff that I'll talk about after the break are they're heavily used in our codes, and they're specifically needed, but there's really not ways to do some of that stuff in other programming models very easily. And these 3 points are basically very important for us. The loop bodies have to be unchanged as much as possible. That's where most of the intellectual energy went into these codes, right? People can write for loops all day, but the actual physics that's in the loop, that's the hard part. Has to work with the existing code constructs. We don't want to disrupt their existing data structures and have to tear all that apart. And basically allowing applications to customize these constructs to make it more natural for them. And in fact, the way all of our different codes use this, they actually wrap it in layers in different ways to make it more consistent with their coding style. For example, if it's a finite element code, they've got the notions of looping over elements and vertices around an element and doing things on quadrature points, right? That's not something that's expressed just naturally in a for loop or something like Raja, right? But they want to be able to capture that and make it intuitive for the developers. So as David said, what we're doing is basically promote. When we started this and getting our application developers to use this, we basically went and iterated with them many times for this to kind of wrap their head around it and figure out how they're going to use it. And so we actually developed how we were going to do this and how we were going to design this by iterating directly with our users and getting them to buy into this before they even actually tried it out. But one of the things that was important was to basically disrupt the code as little as possible when you move from one platform to the next. That's why we want to do these types, the execution policies, the iteration spaces where you're defined. Those are objects where you just name them in a header file and you just apply them in your code. And then the code is changed the way it can execute by recompilation, but it doesn't really disrupt the source code. And you can try out different alternatives. So another thing our codes do, most of these are I'm not going to go into the details of these anecdotes, but these are really the way things are used. All of the large codes that use this stuff actually went through their codes, developed a loop taxonomy. What kind of loops do we have in our code? How do we use them? Does this class of loops have a lot of work in each loop or a little bit of each loop? So what they would do, and fortunately, they were at least systematically enough that even if they had 20,000 loops in their code, they maybe only had a few dozen sorts of loop patterns. And the difference was some loops really had a lot of work at each loop iteration, and some were more like, they looked like linear combinations of BLAS routines, very simple stuff. So they would develop these policies and basically annotate their code and then figure out, let's say, okay, I'm iterating over elements in my code, but I'm doing very little work, so I'll have a particular policy for that. Or I'm doing elements, but I'm doing a lot of work in each loop iteration. They would develop a policy for that. So that's how they actually do this. But how they do this is completely up to them. So we just want to be able to support that sort of a development model. So one thing that's different between Raja and other models, Cocos in particular, we don't provide a memory model. And that was kind of by design. We still think it's a good decision. And I'll say a little bit why we think that. So the users are basically responsible for managing their memory spaces for heterogeneous architectures, CPUs, GPUs, that sort of thing. So when you write a kernel like this and you're going to try to run something on a CUDA device, say using a CUDA execution policy, users responsible for making sure A and B arrays are accessible on the GPU. So how did they do that? Well, there's several choices. You can do it manually. You can put CUDA mallocs and mem copies all over your code to move data back and forth. You can rely on unified memory model that CUDA NVIDIA provides. Some architectures have it supported in hardware, which is good. But there's still performance issues associated with that if you trust it too much. You still have to be careful and pay attention to how paging is being done. Or if it's implemented on software, some commodity GPUs only have a software implementation. That has serious performance implications, so it's not usable in many cases. So one of our applications needs to actually run across those kind of environments. When I was talking about running on laptops in particular, right? They're not going to have typically hardware-supported unified memory. So, and manual memory management is often preferable in terms of performance to unified memory. It's just harder to do, and it takes a lot more attention to detail, and it becomes unwieldy when you have 20 code physicists, walking around in your code and writing stuff, and things are breaking all over the place. So we developed this product that David actually leads called Chai. I'll just mention briefly what that is, but it's a model to provide automatic copies as needed. So it kind of works from the point of view of the application developer like unified memory, but it actually does manual stuff underneath the covers. So you get kind of the best of both worlds. But putting it in it takes time, and you need to figure out how to partition your code to do that, because once you start doing it, you kind of have to go all the way through to the end, because once you start using these abstractions, if you miss one someplace, your code's going to break, and then it could be hard to figure out what's broken. But it was developed to complement Raja, and here's basically how it works. It provides these managed array abstractions to make the data copies kind of transparent. This would, apart from this top part here, it looks the same as if you were using unified memory. So if you have two managed arrays, say A and B, and they're allocated and initialized on the CPU, if you go into a CUDA kernel, the infrastructure knows whether or not those arrays were actually used in the CUDA device environment previously. And if not, they will be copied down to the GPU memory, okay? And the reason the A is grayed out here is because after we do this computation, A is not going to be the same necessarily on the CPU as it was updated on the GPU. And if you come back and you run something with those same arrays back on the host, it'll copy A back, but it won't copy B because there's this const semantics involved here, and it obeys those. So if you know what you're doing in your algorithm, you can get some optimizations, not copying things around as much as you need to. And you can also support unified memory under the covers with this, so you can try unified memory out in your code or do this and actually see how it performs. It's kind of interesting. Yeah.
About the previous slide.
Yeah. This one?
Yes, this one. So when I, let's say I'm the host side and I want to execute this CUDA kernel, then it's going to transfer the memory automatically to the GPU, compute on that. When exactly does the memory copy back happen? Does it? It
would happen again at the next kernel invocation. Yeah, so if you ran multiple CUDA kernels after this, it wouldn't do anything. It would just stay there. It would come back when you change the execution context. So the way it works is underneath the covers, basically through the lambda capture, these things go through their copy constructors, and then it figures out where it needs to move things, okay? And so what happens is it'll know there's a record associated with each of the pointers associated with this, right? I have an active pointer where I was last used based on the execution context, and then I might have other ones, to track this memory is mine on the host, this memory is mine on the device. And it basically does that bookkeeping for you.
Would that allow it to overlap communication and computation?
If it's different data, it's not going to wait, but the copies are generally done synchronously, but we're working on some stuff that would asynchronously kind of move chunks of a huge array through the device memory asynchronously.
Yeah, we're working on another project which is basically a kind of a abstract task queuing model where you can basically queue up tasks, including transfers as well as computation, and orchestrate something like that. But you would manually construct how this would be done.
Because the mem copies sometimes take so much time that you want to overlap it somehow before you actually.
Yeah, but generally with this model, so we have this being used in several codes, and what they're generally seeing is better performance with this than just relying on hardware-supported unified memory by, dozens of %, right? So a couple other things in the few remaining minutes before the break that I just want to go into, and this is something David mentioned about issues you need to be aware of with this. Anything that you're going to use something like a C++ abstraction model and you choose to use these lambdas. We think you could also do this with C++ functors. We don't really want to force that on our users, and they wouldn't do it anyway. So the lambda is basically the lightest weight thing, but there's issues that come along with it, including us continually fighting with compiler vendors about improving their support for lambdas. But the one question is, you have this different way of capturing variables when you enter a lambda. Do I capture them by value or reference? And you have an equal sign or an ampersand, depending on how you want to do that. That's how it's expressed. But value capture is required for GPU execution. Things actually need to get copied into the GPU environment, or when you're using reductions, those objects have to get copied so that we can assign them to individual threads as needed. When using chai, because it has to go through the copy construction mechanics to do the memory transfers properly. So what we generally advise is just use capture by value. And we've done lots of experiments, and it's either always a performance wash or slightly better. So there's really no need for us, unless you're staying exclusively on CPU, for example, to use capture by reference. Another thing, people, and maybe you guys are good enough software engineers, you don't use these kind of constructs, but lots of physics people with grayer hair than mine tend to write loops with breaks and continues and stuff like that, and you can't do any of that with this stuff. It just won't work. It wouldn't work either really in a GPU kernel. So you have to rewrite things if you have that. One issue that we weren't completely aware, we didn't think about it, but it actually bit several application folks initially caught them by surprise, is that global variables are not captured in a lambda. And that's part of the C++ standard. It says that they're not. So when you do something like this, you will get a compilation error telling you that this is undefined inside your kernel. Now, one solution, and this is basically what our application folks are doing, and it's somewhat gross, but it works, is you just make a local reference to it here, and then you use that inside, and so that works. And so what was happening was people started doing this with OpenMP, and they were basically getting lucky because they were using global variables inside their loops, and they were still in the CPU memory space, right? As long as they weren't violating, they weren't writing to them in threaded code or something, they were just fine, and so they were kind of getting lucky. Another issue is that local stack arrays aren't captured in CUDA device lambdas. And this is technically a violation of the C++ standard. I wish, so do our application folks, that NVIDIA would change this, but they're not going to, at least in the near future. I kind of understand why, but I don't agree with it. So basically, when you write something like this, where you just say, okay, here I have an array of some values, and I want to use those inside a loop, that will also be a compilation error. So here's a solution. Well, there's different variants of this, but here's basically the punchline of the solution. If you wrap that array in a struct, with that being its single member, initialize it that way and use it in there, that works fine. You might say, well, why should that work? Well, it just does. It's like, I'm not a compiler writer, but that's how they implemented it. So, but these are things that you have to be aware of, and so we include them. There's a discussion of a variety of these things in our user guide. It's helpful to at least be aware of them before you get caught. The other thing is that anything using a device a lambda in CUDA device code, unless you actually define it inside a device function, needs to have the device decoration. Okay, so when you're using a CUDA execution policy, for example, or even if you wrote a templated global function and passed in a lambda to that, you would still have to do this. You have to put that at the point where the lambda is declared. Now we have a lot of, and you can imagine how this would be useful to basically be able to do this and have a lambda be also used simultaneously in host code and device code, and just have it be available both places. You can do it that way. There's a host device annotation that you can give it. And we have a lot of use cases for this, and we'd really like to be able to use it. The problem is that when you do it and you use that lambda in host code, the CPU code is going to be a lot slower than if you basically just wrote the host code with an undecorated lambda. And there's a technical reason for that. Currently, we worked with NVIDIA compiler people for several months, and they made some progress, but they eventually threw up their hands. Basically, what happens is the lambda gets returned back to the host compiler wrapped in effectively a standard function object. So you incur this heap memory overhead for allocating that, plus a pointer dereference at every loop iteration. So we have some macros to help with these annotations, but there's still this basic problem. Yeah, so the punchline, and this is just a final note before the break, and then we'll come back in and I'll talk about some other more complicated looped kernels and how we deal with them. Performance portability it's hard, and it takes effort, right? So any approach, regardless of what it is, and like Raj in particular, it's our attempt at an enabling technology, right? It's not a panacea. It's not going to solve your problems. Hopefully it'll make a lot of your things you want to do easy and make hard things you want to do tractable or manageable. So you still have to think about loop characterization, how much work am I doing in loop iteration? What do my memory reads and writes look like? How much available parallelism? Do I have branching? All that kind of stuff. You still have to look at that. And performance tuning, all manual processes. You need good tools. In all cases, memory motion, especially in heterogeneous architectures, is critical, and you have to pay attention to it. As I said earlier, NVIDIA now supports on certain GPUs hardware, unified memory and hardware, but it's still much, much slower than doing things manually. I think the cost of currently on the Voltas that we have on the new Sierra system and the Summit system at Oak Ridge, like a CUDA malloc manage is many times slower, dozens of times slower than a CUDA malloc, which is 100 times slower than a CPU malloc. And a CUDA free is I think it's 100 times slower than a CPU. You have to be aware of these things, right, if you're doing a lot of memory stuff. Application coding styles will probably need to change regardless of what model you choose. We're trying to minimize the impact on these big behemoth codes that we currently have, plus enabling other codes to get started with something that works, where we've thought a lot about this. In particular, the things you have to think about is you might have to change your algorithms. Writing algorithms, where you didn't need to think about finer grained parallelism, say, than MPI, may not work when you introduce thread parallelism or GPU parallelism. You might have to change so that they run correctly in parallel, which might mean recasting some patterns as reductions where they weren't reductions before, or parallel scans. Parallel scan, you might learn, will become your friend. A lot of our people at the laboratory who write advection algorithms where they need to count zones in a particular material and that kind of stuff. I say, oh, this scan stuff's pretty cool. I didn't know what that was before. But it helps them. Another important point, this is hard to do in a large code, but if you code this way from the start, it's very helpful, is moving your variable declarations to the innermost scope can help avoid a lot of thread correctness issues. And virtual functions and the C++ standard template library tend to be problematic for GPU execution, not really super supported well, especially with virtual functions if you cross the host device boundary. I think Cocos, I was talking to Christian a couple of months ago, I think they're working on trying to come up with a good solution for that because they have a need for that in their application codes. I'm not sure exactly what the status of that is, but it's a problem. And for us, we're taking the approach, simpler is almost always better, right? Use simple data structures, types, and arrays, and especially when you're closer to the computation. Use complicated, object-oriented parallelism and stuff to manage higher level complexity in your code. David mentioned earlier we have stuff in Raja for simple loops, and he presented most of that. So those are just loops that we think of as kind of simple, non-nested for loops. But we also have infrastructure that we've been developing for several years, and we've been iterating on it. And this is our third pass through the API, and we think we like the API right now, but there's still some details we're arguing about. And these changes come about by actually putting it in a code and then realizing that we didn't think through something completely. But basically, we're trying to develop an infrastructure for supporting kind of very, very complex loop kernels. So to motivate what we're going to do, basically, I'm going to focus on a nested loop example. There's lots of other things we can do with this that we do, but this is, I'm going to go through kind of slow. It takes a while to kind of wrap your head around it. So a simple nested loop example. So here we have a simple matrix multiplication. You have 3 matrices, just simple square matrices, A, B, and C. C is equal to the product of A times B. So this is one way you would typically write it in C. You'd have we're assuming kind of a column major ordering here, and you iterate over the rows on the outer loop, then over the columns, and then you have this inner part of your kernel where you're basically computing a row-column dot product of A and B, and then you write the answer back out to the appropriate row-column index in the result matrix, okay? So think about what we've seen so far. Well, since we showed this for all stuff, we could try nesting them, right? By basically writing a outer for all and then an inner for all. We've got an outer range and an inner column range, and then we've got a loop index variable for each. And for the most part, with certain policy choices, this works. However, there's problems with it. Particularly if you notice this, and I remarked on this for an earlier question, the way Raja works is the for all machinery is basically completely decoupled from what's inside the lambda internally. They're completely decoupled. The inner part is what the application person writes. The implementation of the the for all stuff is what we write. And so when you do it this way, each loop level is an independent entity. So parallelizing them, those two outer row and column loops in any kind of coordinated way is hard, unless you have other stuff, right, where you expose certain maybe data structures and pass a handle back about something so the inner loop can figure out how to coordinate its parallelism, et cetera. Or there's other tricks. But we didn't really want to go down that road. Another problem it has is you could parallelize the outer loop, let's say OpenMP or CUDA or whatever, but then the problem is all of the stuff inside the inner loop is executed sequentially inside each thread, right? So you're leaving a lot of parallelism and performance on the table. You could parallelize the inner one, but then you have this potential synchronization for each outer loop iteration if you parallelize these things separately, right? You're launching a separate parallel computation for each row. Plus, once you have this, if you look, suppose you wanted to transform this in some way. Let's say you, on one architecture, it would be better, in one data layout, it might be better to have the column loop on the outside versus the row loop on the inside. In order to do that here, you'd have to actually change the source code. So that kind of breaks our encapsulation model that we want to preserve with Raja. So we don't recommend for nested loops and more complicated kernels to try to jam anything into for all or do funky things with for all. So I'm going to go through this in more detail, but I'm just kind of putting most of it up on a slide here. And this is about as simple as example as we can get on one slide. So this kernel API that we have is used to compose and transforms more complex parallel kernels. So the key difference to focus on first is we have a single construct called Raja kernel. It's got a policy. And then for like a nested loop case like we're talking about here, I'm only doing the outer loops right now. We have a tuple of iteration spaces, a range for the column, a range for the row, and then the lambda itself has two arguments, one for each iteration variable associated with those iteration spaces. And then we have stuff up here in the policy that I'll go through in some detail. But the punchline so far is so it's all in one construct, and for this example, the lambda expression for the inner loop is the same as what it was in the previous slide where we nested the for alls. So for this stuff, and you'll recognize that it's very similar to the for all stuff, there's four basic elements. You still have a loop execution template. In this case, it's kernel, not for all. We have loop execution policies, right? The kernel policy is going to compose these policies in a way. Basically, you prescribe a policy for how you want each level of the loop nest to be executed. You have loop iteration spaces, right? One for each loop level. They're just range segments here. And then you have a body, which could be multiple lambda expressions. So concepts are all the same. What kernel does is it basically, it's more complicated than this, but they're basically variadic templates now where you have multiple policies, multiple iteration spaces, and multiple lambda expressions to compose the loop kernel. So as I mentioned, each loop level has an iteration space and a loop variable, right? What we have here. And we have this tuple machinery. And the reason we do it this way is because we internally, we take this tuple, we know it's the first argument, it's going to be some ranges, and we pull out the arguments and we massage them, or we stick them in at the appropriate locations. And this tuple supports, basically, these can be different types where, a list or a range or whatever. And so this is basically some veneer over. We have another kind of library that we're developing called CAMP, which will appear on GitHub at some point. It's been recently released. We're basically developing bits and pieces of an actually portable template metaprogramming layer that's actually portable. So it's kind of like a C++ version of bits and pieces of the STL, but that actually is portable across programming models, and it works in GPU environments and stuff like that. So one important point to note about this is that for the tuple iteration spaces and the arguments to the lambda, those things need to match. The type has to be the same. If this is an integer range, this has to be integer. Columns correspond to columns, rows correspond to the rows, and that's important because it's how everything gets composed. Oftentimes we can catch some of these things at compile time. We also provide typed indices that I'm not going to go into here. You might see some of those if you actually dig around through some of our unit tests. We don't have those illustrated very well in examples right now, but it helps people who are writing complicated code with like heavily nested loop. But we've got codes with 6 and 7 level nestings, loop nestings, which is what motivated this. And if every one of those loop indices has its own type, you can catch at compile time issues with if you program something incorrectly. So if you notice in these for statements, they basically abstract the notion of a for loop. They have these integer arguments, template arguments at the beginning. And those correspond to their indices in this tuple. So this inner guy corresponds to the column range, and then this is the policy associated with executing that column loop. The 1 corresponds to the row range, because it's in the next one, and then that policy. So that's what it is. So those indices indicate the tuple item, the iteration space that it applies to. And so now what we can do, once we do that, remember we're trying to encapsulate things. Before, if we nested for alls, we couldn't, let's say, swap the ordering of the loops. If you wrote standard C code, you couldn't swap the order of the loops without rewriting those loops, right? But what we can do in the policy now is we can just switch these statements for the fors, right? So the only difference between these two guys is I just basically swapped them. This one runs the outer loop, the row loop on the outer side, index 1 in the tuple, and the inner column loop on the inside. And the bottom one runs the column loop on the outside and the inner loop, the row loop on the inside. Okay, so now we can start to do transformations, and with different data layouts and orderings, we can start to use views and compose things. And you write that algorithm code once, and you can swap out things, just replacing types in header files, and now you can recompile the code to have it run all kinds of different ways. Okay, now this is a little bit more complicated, and I'm just using this to illustrate the point. But you can compose the kernel from any number of lambdas. Okay, and there are examples if you look in the examples directory in Raja, there's a whole sequence of this example done in different ways that you can actually play around with and look at. But so what's going on here now is we have 3 lambdas. We've got the first lambda represents the initialization of that dot product accumulation variable. The lambda 1 is basically the inner body of that inner dot product loop. And then we've got the outer lambda, which is writing that dot product to the result location. And the reason you might want to do this is now we could actually apply a Raja loop construct on this inner guy, right? So we have then 3 ranges in the tuple. We have the column range, we have the row range, and we have the dot range. And then we also need, for parallelism, we need a thread local variable. So we support this kind of stuff too, which is why there's this param underscore argument. So if you have any thread local variables, they have to come after the ranges, and then you use the kernel underscore param, okay? And the other point is here, when we do this, because basically we're taking these things that are described in the policies, we're constructing the kernel, and then we're passing arguments to each lambda. And the way we do that, to not drive ourselves crazy, we pass in all of the arguments to each lambda in the same order. But you'll notice that you don't have to use them all. right? This only uses the dot product to initialize that. This uses the column and the row and the k index, right? Because it's inside of all three loops. It doesn't use, well, it does use that one, so it uses all of them. And then this one only uses the column and row. It doesn't use this k, okay? So once we have that, now there's other things we can do, right? So here's the policy for that. And it's kind of, if you're not really familiar with looking at, heavily templated, variadic template code, it's like, what's going on here? But it's really just analogous to how it's indented to make it look like, think about nesting that original for loop and replacing the fors with these Raja statement fors, these chevrons with curly braces. Take the code for each lambda and just slap it in here. Here's what you get, right? So what I'm saying here is my policy is I have two outer loops. The outermost one corresponds to the range of the first entry, or the index 1 in my tuple, and I have that policy. This is the 0 entry in my tuple, and that's the policy. I'm invoking that first lambda. I have another loop, and it corresponds to the range of the third argument, 0, 1, 2, in my iteration space tuple. Inside that, I plop the code for that lambda, and then I basically do the second lambda after, and then I just close everything up, right? So it's, once you kind of wrap your head around it, you can see what we're doing. We're basically packing these arguments into structures that we can pull apart and compose depending on what those policies are, and build up kernels inside of the code. So for example, you can do like OpenMP collapse sort of stuff, right? This inner stuff is the same as it was in the previous example, but we have a collapse policy, and you pass it an execution policy that says, I want to apply OpenMP parallel collapse, which basically is effectively the same as if you're familiar with OpenMP, the collapse argument that you put on a pragma, you say how many loops you're going to collapse. So we provide this arglist construct which tells you which loops you want to collapse. And for the purposes of this construct, we assume that these are perfectly nested loops for the collapse part. And then this tells us what order they're going to be, right? The convention is the outermost one here is the innermost one or the last one is the innermost one. So just as you nest your loops, it's 1, 0. So it's the same order as it was in the actual straight C code. And so this policy will distribute the iterations for both of those outer loops across the CPU threads, and however the OpenMP implementation does it. But we can do all this now. We're just working with the policy, right? We're outside of the actual source code where the kernel stuff is. And we can do things with CUDA. So we have a CUDA kernel construct where now we're saying, and this is a point I just say right now, this may change a little bit over the next, I don't know, we're still arguing about this. But what we're doing here is what we settle on for now is we're basically saying take the iterations in this loop, that row loop, and distribute them over CUDA thread blocks, just using the regular CUDA parlance for CUDA policies, and distribute the column iterations over threads within each block. And so that's effectively the same as if you just peeled this apart and wrote a CUDA kernel, in a global function with all this stuff put inside it. You would divide your row and column indices using that CUDA dialect down there. So here's just another example. So what we're doing here is the same kind of thing. We're keeping all the same ordering and everything, but we're distributing the iterations over two-dimensional thread blocks of some size parameter that we get. That it's BS, but it means block size. I just didn't have enough room to put. But that's what it means. It's block size times block size. So it's a two-dimensional thread block now. So you can imagine if you had nested loops 3, you could apply a three-dimensional thread block and do all kinds of things. So what we're really doing here is just, if you want to boil it down to its bare bones, it's really combining what we call statements and statement lists. So a statement is just an action. And I'll describe the statements that we currently support. It's execute a loop, abstract the notion of a loop, invoke a lambda, right? Set a thread barrier, for example, right? So for example, just lambda 0, that means invoke the first lambda in the argument list. And then a list is just some ordered list of statements that gets processed. And where you have the policies, you insert the appropriate stuff for a for loop according to that policy, and you put the stuff inside it within that loop. So this is a statement list, right? We've got a for loop corresponding to the 0 iteration space. Here's the execution policy. Inside, we invoke the first lambda in the argument list. Then we have another one which uses the 0, 1, 2, so it's the third iteration space in our tuple using this policy, and then we invoke the second lambda, 0, 1, in the list of lambdas in the argument list. So what we're basically done is constructing kind of a simple domain-specific language, but it only relies on C++11 support. There's no code generation going on. The compiler's writing all this code, or what the ultimate executable is based on how you prescribe it. And you might say, well, this seems very detailed and prescriptive, but that's kind of how our application developers prefer it at this point. And remember I said that the application teams that use this stuff tend to wrap it? What they do is they wrap these policies and some of these constructs in their own abstractions, and then the application developers say, okay, I have a 5-level nested loop, I'm gonna apply 5-level nested policy, and they don't even have to think about what's all going on there, and it just works, okay? And a kernel policy is just a statement list, right? It's a collection of statements and enclosed statements, which is a statement list. So we currently support a variety of different things, and these are just being built up based on use cases. And we've got some more in the pipe right now that'll be rolled out in the near future. So we have a for abstraction, right? It takes an ID for what iteration space it is, a policy, and then whatever's enclosed after it, basically the stuff that would be in that loop before you put the curly braces, although it's closed with the chevron. A lambda, just evoke a lambda expression. We have a collapse policy, right, where you have the policy, and then which loops I want collapsed, in what order, and then all of the stuff that goes in it. And they have to be perfectly nested to use that particular thing. We have an if conditional. So we use this, you can actually write out a complex policy in a kernel and selectively choose parts at runtime based on some kind of runtime conditional. So what we do here is we play around with, and users are still getting used to this, and they found out ways to use it in certain types of algorithms. You can, in certain situations, say, depending on how, I've got a sequence of loops, and depending on how long those loops are, but they all have the same index space, I might want to fuse them all together, or I might want to break them apart, right? So you can use this to, at runtime, select whether I want some kernel to be done where I'm fusing a bunch of loops together in a single parallel execution context, or I'm breaking them apart into multiple ones. We've got a CUDA kernel, which is basically just launch the code inside as a CUDA kernel. We've got sync threads. We've been focusing mostly on getting things running on the Sierra platform on the GPUs, so we didn't do a OpenMP barrier, but we'll have a sync threads for that too. Then we have some more interesting stuff that has significant performance benefits once you learn how to use it. And this, I have to admit, we haven't really built up good examples or user documentation for this stuff yet. That's coming. We have it exercised in our unit tests, but if you look in there, you might start, if you try to understand it too hard, you might try to start elevating above your body, and it's kind of it warps your mind a little bit. We need to do a better job of documenting this. But anyway, we've got things where you can basically use shared memory, either on a CPU, or where you would do something like cache blocking, or use CUDA shared memory on a device. But this simplifies the fact that you basically set a window, and internally you can share a shared memory buffer, across blocks of threads, a grid of thread blocks, and you don't have to do any manual indexing. You just have to make sure you're doing the right code to write stuff into that and setting your barriers properly. We have tiling policies for you to do outer tile policies on loops. And we have a hyperplane policy that we're using in some deterministic transport applications, which actually do like diagonal sweeps across grids. And so you can write that without actually having to write all of the loop and where the parallel synchronization has to work out. Anyway, this stuff, I'm just throwing it out there that we have this stuff, we're exercising it in real codes, we just don't have it really well documented. And we're going to be adding more types. We need to bolster our shared memory support. There are certain things that we currently don't support very easily. We're working on that. Another thing that we need that we don't support currently is the way this works now is this nesting stuff has to be compile time defined. So for example, you can't have an inner loop whose iteration space depends on an outer loop iteration, for example, very easily. But we have other constructs to enable that. We just have to develop the machinery to do that and some extra statement types. But anyway, so basically the support, we're basically focusing on what we need to get our applications running. So that's what we've been doing, the OpenMP, sequential, SIMD, CUDA stuff. Believe me, when you actually write code this way, it's amazing how you look at it and go, is this too much crap to throw in front of the compiler? But compilers actually do pretty, it's like if you add more and more abstraction, performance gets worse, and then you get to a cliff, and it just, they all of a sudden understand it, and then they write really good code. This stuff really vectorizes well. We're still working on some of the OpenMP target support, and the TBB and ROCM stuff is work in progress. You can see how that's a common theme in our support simply because we haven't been focused on those. So anyway, I'm not going to go into the views and layouts, but somebody asked about that. They're in these slides that are on the website. Let me just go to the end here, kind of wrap up. So here's kind of the summary stoplight chart of where we currently are. So this basically, juxtaposes all of those different stoplight charts that we had for all the various sections. Our support is fairly complete. We're still filling in some gaps. We just recently working with AMD on this within the last year, but it's getting there. Let's see. So just to revert. So there's supplemental materials to this tutorial. There's a bunch of working examples. David and I don't really have a plan for the hands-on session this evening, but if people want to come in and try to run them or walk through them or ask questions about them, we'll be available for that. Or if you want to try some of this stuff out in your own code, we'll be here to answer questions. They're in our repo. We have our user guide that is linked to from the main GitHub page. I wouldn't try to remember these other URLs, but all of this stuff that we've talked about plus more is kind of described in detail. We have this proxy app suite that's kind of a work in progress. We're trying to collect Raja variants of the proxy apps that are representative of real codes that we can't show to vendors for machine procurements because they're actually coded in Raja, and so we need a way to be representative of them. And we have this performance suite that we mentioned. Chai is another thing that's also on GitHub. And then if you have any feedback, questions, we appreciate it. This is our contact information, our Google group if you want to join, or our regular email list. And questions, if anybody. Thanks for listening, participating. Anybody have any questions?